It's my pleasure now to introduce Doug Arnold from Meinberg. He's going to be the moderator of the panel that's going to start right now. Doug?
Thank you, Pat. So we have a panel coming up to talk about obtaining and proving that you have compliance to standards. I have three gentlemen up here, two of the world's leading timing experts in Marc, Weiss, and Lee Cosart. Marc has so much experience he can give anyone's talk. And also Peter Lankford was a leading expert in how to measure various aspects of trading networks and systems as well. So I'm going to have each of them make a short presentation. I asked them just to prepare a couple slides, present kind of one idea, but then we'll have time afterwards where you can ask them questions, and maybe we'll get a couple perspectives on each of the questions. So with that, let's go to the first. Okay, good. Let's see. Okay, we're going to start with Marc. So you go ahead.
Okay. I'm Marc Weiss. You haven't seen me yet today. And the UTC comes from a national lab. Why don't I get the clicker, I guess, so I'll click my way through it. How do you get UTC and how do you prove you have it is the question. And first of all, where do you get UTC from? Well, SEC says you have to get it from NIST. So how do you get it in the door? Well, GPS is actually UTC from USNO, but because USNO is continuously measured against NIST by certainly at NIST, and I assume they do it at USNO. You can now use that if you get those data. Now you have traceability via GPS back to NIST, and it's good to much better than a microsecond. It's actually good probably to 10 nanoseconds. You could get UTC directly from NIST if you ran your own fiber. You can't do it through the public internet unless you want 10 to 100 milliseconds of accuracy. But it would be very hard to document and validate what you have. There are other methods possible, but GPS, even within GNSS, GPS is currently the dominant way of getting UTC in your door. And then how do you prove it? Well, what are the problems? What do you have to look out for? Well, here's a list of things that you have to. So the GPS receiver will essentially account for the delay from the satellite to the antenna with certain assumptions. You've got to make sure that those assumptions are valid. The receiver won't do that for you. So one of those assumptions has to do with what's happening in the free space. I say the air, but really it's empty space mostly from the satellite to the antenna. And one of the effects that could happen is jamming. And a small amount of jamming could cause you to not realize you're being jammed, but to have errors in your signal. And then you probably need to document and validate that you've done a reasonable effort to detect and mitigate spoofing. And that's a big issue that we're not really addressing today, but I think we could spend a whole day on that. And then a big source of error is that your receiver and antenna are set up properly. One of the major sources of error is people putting antennas in the wrong place. They have an electrician put up their antenna along with all the power systems, and they put it on the side of a building with electrical transformers all over it, and you get garbage. And also, you have to have the right coordinates, the data in the system have to be set up right. So that's the configuration. And then you've got to calibrate everything. The delay through the antenna has to be calibrated and known. The delay through the cables has to be controlled and known. The delay through the receiver has to be known. And then any cables coming out of the receiver going to your grandmaster have to be accounted for also. And you say, well, if you only need 100 microseconds, how hard do you have to work? Well, we've also heard that 100 microseconds is not what you really need. Maybe it's 1 microsecond. And some of these things can actually produce large errors, much larger than you would expect. So here's a cartoon of what I just told you. So here's the arrow coming from the satellite going to the Earth. So the satellite itself can have errors. And how many people have heard of 13 microseconds? 13 microseconds. So January of 2016, the GPS system had half the constellation uploaded with wrong data that told you they all agreed that the time was what it was, but it was 13.7 microseconds off of what the rest of the constellation was saying. So you couldn't use majority voting. It's an issue. So you have to worry about the satellite, and then coming down from the satellite, it goes through the ionosphere, goes through the troposphere. Stuff can happen there. We can have very large effects from the sun. And then right at the receiver, there's jamming and spoofing, and you've got to do something to monitor and mitigate and document what's going on throughout all of that. And then when it comes into your building, you've got, this is what I would call user-controlled receiver issues, the multipath or bad installations around the antenna, jamming and spoofing, and then the delay through the antenna, the delay in the antenna cables, the delay through the receiver, and then the receiver configuration, coordinates, receiver software. And my last slide is GPS, GNSS are extremely accurate, extremely reliable, and that is perhaps their best feature and their worst feature. What's wrong with being very accurate and very reliable? Because it's not 100%. And so you depend on it and you don't back it up, and then one day it fails and the signals are vulnerable. So that's what I got.
Okay, good afternoon, everyone. Lee Cosart, Microsemi. So let's say that you've done everything Marc has suggested and you've installed all of your equipment properly and you've got some good time coming in through your GPS receiver. What I'm going to talk about is how we can maintain and assure that good time through a couple of different mechanisms. Okay, so one of them involves combining GNSS with an atomic clock. And the second one is actually addressing the GNSS directly, how we could produce hardened GNSS. And you've heard something about both of these topics, but I'll go into a little bit more in my next couple slides. So first, the combination of receiving GNSS for time along with an atomic clock. So that's a fairly powerful combination. One of the great things about an atomic clock is that it is autonomous. So it's something you place somewhere and it is not going to be affected by anyone trying to do jamming, spoofing, or anything like that. It's a very good source of frequency, so you can't rely on an atomic clock alone for delivering time, but combined with GNSS, it is quite a powerful system for establishing and maintaining time. One of the important aspects of this is illustrated in the plot below, on the left, below the block diagram. That is a requirement for what we refer to as the enhanced PRTC, primary reference time clock, a standard that has been recently developed at the ITU, and it is required to hold over a 14-day period better than 100 nanoseconds. So what enables it to do that is this autonomous primary reference source, the atomic clock. So the atomic clock itself is got very good stable frequency and accurate frequency. The development of the EPRTC actually required that the ITU also develop a new atomic clock. So there is a higher performing atomic clock called an EPRC, which serves as the atomic clock function. And that is a clock that delivers 1 part in 10 to the 12th. So for those of you that are good with performing calculations in your head, you would note that an atomic clock with 1 part in 10 to the 12th frequency would move 86.4 nanoseconds over a day, because there are 86,400 seconds in a day. So you might ask, how can a clock that might move 86.4 nanoseconds in a day hold 100 nanoseconds for 14 days? And that's where we get to the powerful combination of the GNSS plus atomic clock, because while you have GNSS, the atomic clock can be studied, and if it happens to have 1 part in 10 to the 12th offset from UTC, that can be compensated for in the event that GNSS is lost. So as long as the required stability is there in the atomic clock, a system that combines the GNSS and the atomic clock can hold 100 nanoseconds for 14 days. Finally, I'll point out that if you have a better autonomous primary reference, if you have a better atomic clock, then you can do even better than hold 100 nanoseconds for 14 days. So with, say, the best atomic clocks available, you might be able to hold 100 nanoseconds even for a time period of 80 days, and that is something that is under study at the ITU. Okay, on to the next aspect of maintaining time, and that is the Gnss Firewall. You've heard something about that, but I'll review some points there and talk to a few of the details. So there is a system there that once again, in many senses, takes advantage of the fact that if you have an oscillator and you have some smarts and software as well as GNSS, you can build a system that is resilient. Particularly if you attach a very good oscillator, such as a cesium clock, as illustrated in the block diagram, you can do even better. So how would such a system work? Another thing that a timing receiver can take advantage of is that it is a stationary installation. So it is not moving in position. So if something from GNSS is indicating the position is moving, then that's a red flag in and of itself. There are a few other red flags that can be identified. One of them is there are very specifically defined formats for the GPS and other GNSS signals. So the brains inside of such a device can make sure that these formats are being followed properly. As we have heard, the signal level of GNSS is extremely low. So if someone is trying to spoof a GNSS signal, there is some likelihood that the signal levels might not match exactly those of the real GNSS signal. So this is another aspect that can help to identify that there is something wrong, and we'd better turn this GNSS off and use a hardened backup instead. So that pretty much covers it. We make use of oscillators, we make use of knowledge of the GNSS system. We have put all of this together, and in so doing, produce a hardened GNSS system.
Thanks. Is it okay if I go to the podium? I'm having trouble seeing the monitor from over here. Is that okay if I go to the podium?
Yeah, let me just switch with you.
Oh, okay. Even better. Could you bring up the text? Oh, it's mine. Oh, okay. Green. Oh, how about that? Well, first of all, I'm glad that Doug made clear that I'm not a timing expert per se. To the extent that I have any expertise, it's in testing and measurement, and probably more importantly, in getting experts together in areas like timing, as well as other areas, and getting them to develop standards and supporting tools around testing and measurement. Grateful to Matthew Knight from Atomico this morning. He gave a little bit of an outline of what STAC does. But for those of you who weren't here, and to embellish on that a little bit, we facilitate something called the STAC Benchmark Council, which is a large group of banks, brokers, exchanges, hedge funds, and other financial participants, as well as vendors that supply them with strategic technology. And this council has a couple of missions. And the first is around benchmarking, defining these benchmark standards and tools to implement them. And we'll talk today about time accuracy and other related concepts like capture capacity in systems that are capturing events. But the council is actually quite broad. It looks at a lot of different low latency, big data, big compute workloads, all sorts of engineering challenges in finance. I just have a couple of slides to talk about some of the challenges and leading approaches to proving timestamp traceability. This has been largely driven by MiFID II in Europe, which I would venture to say is a bit farther ahead than the CAT NMS plan in terms of what it requires from regulated firms. So the concepts all translate, but the magnitudes and some subtleties will be different. So there are a lot of regulations in this industry. This is an extremely regulated industry. So having a whole bunch of new regulations to look at is nothing new. What is fairly unique about the MiFID II RTS 25 timestamp regulations and the timing component of the CAT NMS plan is that you don't just have to comply, you have to demonstrate that you can comply, and that's trickier than other regulations. And the reason is that the regulators in this case don't actually have the technical expertise to judge whether or not you're in compliance. It's not like they have a bunch of timestamps that are accurate on those events that you're reporting and they can compare them to yours, because if that was the case, they wouldn't need your timestamps, right? So the only way to judge the quality of the timestamps is to judge the quality of the implementation. And that's just not a skill set that regulators have. This, I don't know if you can read it, this little call-out box is a regulator looking at all of the firm's network diagrams and test protocols and so on, and says, hey, your path delay could be off due to queuing in switch number 14. I mean, those are words you're just never going to hear a regulator say, right? And by the way, we're talking about timestamp accuracy, not just clock accuracy. So we're talking about the accuracy when a timestamp is applied to an event relative to when it actually occurred on UTC. This is more complicated than just the getting quality time to a site, because you have the entire distribution path through the enterprise, and then you have it's either being timestamped at the application or at the network level, and so there's lots of different sources of error in that timestamp. And also, I'm not sure how it works in the US, but in the EU, the burden of proof for any regulation is on the regulated firm. So you have to prove that you are in compliance. A little different than the innocent until proven guilty paradigm we're used to in the US. What that means, in effect, is that when the regulators ask for some trading event data, let's say there was some sort of mini flash crash or something, or they're looking into market spoofing or front running or some other sort of suspected behavior, market manipulation, and they ask your firm for data, they're going to say, okay, along with that, give us the evidence that these timestamps are reliable, accurate, that are applied to these events. They will also, they've told us, at least the UK regulators have told us, that they plan to do what they call thematic reviews, which means they'll just select some firms and go out and just look at their time stamping mechanisms and solutions and see whether or not they're in compliance with the regulations. So the fact that the regulations call for certain things that the regulators can't themselves judge is a recipe for confusion and cost. You can just imagine what's going to happen. Like in Europe, what happens is, in a case like this, they issue what's called a Section 166 request, which is they bring in a consultant at the trading firm's expense to dig up stuff, right? And it goes from there. So what is the key to demonstrating compliance? Well, there are a lot of firms that seem to think that if they've got the right components, if they can tick the boxes on the buzzwords, that's sufficient. And our view is that that's not the key to compliance, and the regulators we've spoken to agree. Great technologies can yield bad results. I mean, Chris Laura's presentation from Pico was a great example of a number of things that can go wrong when you actually deploy stuff in an enterprise. So just saying, oh, we've got excellent master clocks, they've got rubidium oscillators, and we're using PTP version whatever. Just saying that stuff is not enough. It's kind of like actually, Chris also had the analogy of an airline. If you're supplying a new jet engine to an airline, and they say, how can we have confidence this thing works? It's probably not enough to say, well, we use the highest quality metal you can use in a jet engine, right? I mean, it may be necessary, but it's not sufficient for sure. The key, in our view, and the view of this group, is testing and monitoring, actually empirical data, right? Because these tell you how the solution actually works. Why would a regulator trust your testing and monitoring is the follow-on question to that. And the view of the STAC Benchmark Council, not surprisingly, is standards. When you get into that area of finger pointing and confusion, it's really helpful to have some industry best practices that have been codified, not just on paper, but in software tools and processes. So as far as I'm aware, there are two bodies that have developed and are developing standards for this kind of stuff. One is a clock sync working group within the fixed protocol organization. And that group has focused on a lot of questions about best practices in terms of what to use, what not to use, but more so now that they're actually working on a document around best practices in monitoring. And then there's STAC, which is what I represent, with its STAC TS suite, which is for testing and reporting traceability. I'll just give you a quick overview of that. So the starting point for this is a working group, the STAC TS working group, which consists of a lot of time sync vendors, event capture vendors, network vendors, and so on, as many of whom are in the room, as well as the user firms themselves, HFT, high-frequency trading shops, and brokers and exchanges, some of whom are also in this room. And that group defines the standards that then get turned into software that often leverage components, hardware components from a variety of firms. And the group has divided the challenge of time synchronization into 4 big chunks. There's time distribution to site, which is most of what everyone's talked about today, getting accurate time to the site. And then the next chunk is enterprise time distribution, getting it throughout the enterprise, which can be simple or complex depending on the situation. And then the final bit is actual time stamping, and that can happen in an application, software application, or can happen in the network, in some piece of network gear. So there's application time stamping and network time stamping. So there's a lot of methodologies developed to test those pieces. And then there's a framework for pulling those test results together with real-time monitoring data to do a statistical analysis to understand what the total traceability is of a particular timestamping point over a particular time interval, and also what its sort of normal operating range is. I mean, one question you might ask is, well, if you have monitoring, why do you need testing? And the short answer is that monitoring tells you what happened, but it's a rearview mirror. And most regulators are not going to believe that driving in the rearview mirror is best practice. There are certain things that you can't monitor. When a component goes into holdover, in other words, there's no time signal, it's not under time discipline, how do you know how far off it can be over some period of time? And the answer is from your testing you've done, right? Another example is at the application layer. What you find in a lot of applications is that the amount of jitter in applying timestamps, the delay in acquiring a timestamp, often is far larger than the error in the time signal coming into that box. And there are ways to mitigate that and so on, but understanding the entire error in the timestamp requires looking at a whole lot of factors. So those are my prepared remarks. Doug, back to you.
Thank you, gentlemen. So hopefully you were thinking about some questions, follow-up questions during those, and we would like to invite you at this point to pose those to the panel that we have.
Hey, Peter, really appreciate the rundown. It's really interesting. You're looking for anomalies, obviously, in the trading path. I'm just curious, as kind of along the lines of the question I asked earlier, do you, in your testing, do you come across any third-party nefarious behavior altering timestamps in the path?
What do you mean by third party?
I mean, like a nefarious party who's trying to change a timestamp for somebody else. In other words, the timestamp is, this transaction is taking place through the network.
Oh, you mean like a bad guy?
Yeah, exactly.
Spoofing, that kind of stuff?
Exactly, spoofing, so that all of a sudden, you modify it in some way.
Right. So well, first of all, in terms of real-world experience to date, so these standards are just rolling out now. People are starting to put them in place, so we don't have a lot of, and actually we won't get a lot of test results from trading firms. They'll keep that internal until a regulator asks for them. There's really no interest in them sharing those. But the test scenarios include those kinds of situations. So if you look at a clock, for example, spoofing, jamming, there's different kinds of spoofing and jamming that can happen. There's a suite of benchmarks around that. That is an area, though, that is ripe for ongoing improvement in the standards. So one of the important things about STAC TS is it's not it's not going to be a done deal. It's a process, and as people get more familiar with things that can go wrong in the environment, they'll want to come back and throw that in to the tests. But that's an important aspect, I think, to compliance. The regulators, at least the ones we've spoken to, don't expect perfection. What they do expect is best practice. So if you can go to a regulator and they show them what the accuracy profile was of the timestamps on the data they care about, if there are exceptions, it's not necessarily the end of the world, especially if you can show that you had test data that showed you that you wouldn't expect this kind of exception, and you use best practices in testing that, and now we understand there's something else that can affect that. We're going to feed that back to the group, and we're going to incorporate that in the standard. You're in a much better position than sort of, well, I don't know, right? Yeah.
Oh, we got one over here.
Well, I wanted just to add to what Peter said, that a lot of times there's really no operational difference between somebody doing something maliciously and something failing. I mean, every possible failure scenario can be caused by accident, and certainly that happens. So that was just one point I wanted to make. But I wanted to ask Microsemi about their 100 nanoseconds after 14 days or whatever it is. How many days of under 1 microsecond for that device?
Well, let me see. I guess that would be something on the order of 140 days, probably not exactly, but that would pretty much extend. And as I did mention, with a higher performance atomic clock, that 100 nanosecond could be extended.
I mean, 100 days is pretty long. For
Yeah.
Financial services.
Something approaching 100 days, yeah.
Okay, thank you.
Peter, I have a question. You brought up timestamp jitter, which is kind of close to my heart. That really speaks to the resolution of the timestamp clock.
Part of it.
So, yeah, it does. And so I'm wondering if in your process of creating standards, are you going to be recommending a particular timestamp clock frequency like a gigahertz for a 1 nanosecond resolution or 404 nanoseconds for 250 megahertz? How do you, because that goes back to the timestamping physical device that's actually doing the work. How do you manage the differences in timestamp resolution clocks that exist in the marketplace?
Well, two ways to answer that. First of all, the group so far has not seen fit to make recommendations about particular approaches or technologies. Simply the ways of measuring any solution you can put in front of it. But when it comes to timestamp jitter, resolution of the clock is actually a really third or fourth order issue. I mean, you find so there's resolution of the clock. There's the best case delay of acquiring a timestamp, which is usually tens of nanos, low tens of nanos on a modern processor. So that's not really a big issue either for the regulations we're talking about here. But then you start getting into things like cache misses and other sorts of, well, things like cache misses are probably on the order of 1 or 2 microseconds. But then scheduling delays in the OS are the biggie. I mean, and we literally see systems that can be milliseconds delays. And the thing, I guess the important point about MiFID II at least, and again, we don't know exactly how the US regulators are going to look at this, but it is expressed in absolute terms. It is a speed limit. It says, thou shalt not be less accurate than plus or minus 100 microseconds if you're in that category of applications. And so there's been a lot of debate in the industry about, actually there's a lot of pushback on that. A lot of firms said, well, that's not how system engineering works. You can never be perfect, right? So can you say us like 99 percentile, underneath 100, and they said no. In fact, in an early version of the regulations, that's the way it was worded, and they relented, they didn't relent, they went back and made it absolute. So the letter of the law is you can't pass that. And there are, of course, so sort of the gray area is what regulators are going to consider an acceptable exception. But when you're doing hundreds of thousands of event logs per second, which is very common in this industry, 1% of those being wrong is a lot of events, right? And so it's really important to look at the outliers. So we have not, the STAC group has not taken a stance on this and said, well, you need to look at max or you need to look at 99th percentile or whatever. We provide a range of statistics, but it's not about the mean and the standard deviation because these distributions typically are not normal. In fact, they can be really, really unnormal. It's a data-driven non-parametric method that looks at the extreme end, which is what you really care about, and that's where we see when you start looking at the extreme outliers, it can be up to milliseconds. Yeah.
Okay, let me ask the same question from a slightly different perspective. And being European, I'm more familiar with MiFID than with Rule 613. Now, MiFID requires that timestamp granularity is 1 microsecond. Now, it turns out that granularity is not a defined term in the international vocabulary of metrology. So how can one be compliant with the non-existence definition?
So that's an interesting question. I'm trying to remember. I'm pretty sure they've clarified that to mean literally a number of digits. So it does not incorporate a concept of resolution or anything like that. It's simply, we want to see the timestamp out to 3 decimal points if it's microsecond, sorry, 6 decimal points if it's microsecond granularity.
In that case,
It's a pretty meaningless constraint, I think.
let me tell you a horror story. One person I was talking with a couple of weeks ago said that, in his opinion, all events which occur in a certain interval between T0 minus 100 and T0 plus 100 microseconds can be time-stamped with the same number, which means that in that interval you cannot even define an ordering between events.
I'll go you a step further. There's no requirement in MiFID II to have monotonically increasing timestamps. It's possible in some operating systems to get screwed up and have events that are reported in the wrong sequence. And as long as it's within that plus or minus 100 microseconds, it's not against the letter of the law. These are things, though, that'll probably get clarified over time because there are certain inconsistencies. But yeah, I think that's true according to the guidelines. Yeah. And a lot can happen in 200 microseconds in these markets, by the way, which is, I think, I forget who mentioned this morning, they think that it's likely that these regulations will get tighter over time.
So I actually have a question for the panel, and maybe we can get, since all of you come from slightly different positions in industry and government, we can get each of you to weigh in. What kinds of questions, so we were talking about robust systems, what kinds of questions should a network operator be asking the vendors that come in and give a pitch to, for various parts of the equipment that make up a timing network? What are some of the key questions to ask?
Well, I would start with where are they getting, what's the source of their time? If it's GPS or is it NTP or PTP, and if it's through the network, what network is it going through, and how do you know, for NTP and PTP to be accurate, it's a two-way protocol, right? So the delay has to be the same in both directions, and so you would ask the vendor, what network is it going through, and how do we know that it's symmetric? And typically, most folks use GPS to get UTC in the door, and then to have a grandmaster that distributes PTP or NTP through their LAN. And you know that it's symmetric because it's your network and you've built it that way. So those are things that the vendor might not be answering, but lots of questions about your GPS receiver. I mean, how do you know it's accurate? Have you calibrated the antenna? Have you calibrated the receiver? How fast does it walk off in calibration? Do we need to calibrate it once a year, or once every 10 years, or once a week? Those kind of things would be good to know.
I'll speak next.
Okay.
Clearly, some of the questions now, as we become more aware of the hostility in our environment, have to address redundancy, resiliency, robustness, and so on. I think going back in history to some of these events Marc mentioned earlier, the 13 microsecond GPS event, if the vendor could provide some information on how the equipment would perform in such circumstances.
My answer is easy. You should ask your vendor, where's your STAC report? I mean, just to elaborate on that a little bit, there's two ways that the STAC TS standards are getting used. One is firms can use the tools on site to measure their own solutions. And the other is that, I guess there's three ways. Another way is vendors can use the tools on their own solutions in the privacy of their own labs, and when they're ready, they can release results. There's a whole process for that. And the third is that STAC can do these audited benchmarks, like the one we discussed with, or Metamico discussed this morning. You know, to the extent that the standards cover the issues that you care about, you know, obviously we would advocate using them.
Okay, so I think we have time for one more question. So you're the winner.
So, thanks. Considering there's no regulatory requirement as yet in the US from the point of view of timestamp traceability, what does the panel see as the actual drive to implement next generation solutions?
Well, one thing is that a lot of US firms trade in Europe, so they need to worry about MiFID II. But the other is, just from my perspective, and this is not based on any inside knowledge, I think that once the egg hits the fan with a firm that has to demonstrate they're accurate, next question is going to be, well, how do you know? Right? It's the traceability question, and it's just going to be unavoidable.
I'm an outsider to the finance industry, but my understanding is the regulation in the US went from 1 second to 100 microseconds in one step. I would say that's a big wake-up call, and the acceleration is very large in that direction, that it's likely they're gonna, if they haven't demanded something about timestamp accuracy, surely they will do it soon. And they're gonna say, well, 100 microseconds is just the beginning. And it actually, and the literature, I mean, I've read through what the SEC has done and what the CAT NMS LLC is, and you know, it's based on a survey that was done of the industry, and the survey results are really sort of the beginning. In my mind, the survey indicates a fair amount of poor understanding of timing in the industry. And so it looks to me like the regulators, or at least folks who know about timing, who are advising the regulators, are saying, okay, we need an educational process, but we really want to go way below 100 microseconds. So I would, if I were in this business, I would be gearing up to head toward a microsecond today.
You know, it's interesting. Austin this morning from the SEC talked about this body. I thought it was a single individual, but maybe it's a group that is charged with reviewing the standard annually to decide what it should be. And you know, by my understanding, somebody at the SEC said that thing was written kind of vaguely. It says that they'll review sort of, I forget the wording, but something about, you know, what the state of the industry is. And there was the interpretation of that seems to be the state of the trading industry, the regulated firms, where they are in terms of their capabilities. But the original intent was actually the state of the time synchronization industry, vendor capabilities, which may be why Austin suggested that vendors have some input into that, right?
Huh. I haven't thought of it that way.
We'll see where that goes.
We have time for a bonus question? Yes, okay.
Make your life hard. So just in reference to Marc's point, it's actually pretty interesting to read the letters that came into the SEC when they proposed the standards and the comments that people made, because it did show there were an enormous number of firms who had no idea what it was going to cost, what it would involve, and they were treating it like, you know, it was some sort of, you know, Manhattan Project. instead of a relatively simple thing. And you can kind of see the interplay between the sort of lack of knowledge out in the industry, and then the SEC having to kind of deal with that's what their constituents are saying, is plausible. So, hopefully in the next round of it, there'll be more firms that are already, accurate, and there'll be less resistance to upgrading it. But, if you go back and read those, I mean, there are people in there going, this requires us to, hire a whole team of PhD physicists, which, many people would agree is a good idea. But I mean, that was the level that people thought it was going to take. So.
Yeah, it'll be interesting. One thing that'll be interesting to see in the next survey, I remember in the initial one, there were projections on what it was going to cost the industry to comply, right? It'd be really interesting to see where we came in at.
So I want to thank our panel of distinguished experts here. Our next event is going to be a coffee networking break. So if you have more questions or you want to ask individual questions, then feel free to corner them somewhere and have at it. So thank you very much.